It's been such an interesting ride talking about polynomial equations. And in this video, having talked about factorization in the last four videos, we move on here to talk about roots and zeros of polynomials. And this is how this will go. First of all, we look at the basic idea behind roots and zeros of polynomials. Now, uh, as we proceed, you discover that things continue to progress. Having considered factorization, right, we discover that they are very useful when we also discuss about roots and zeros of polynomials. So talking about the basic idea of roots and zeros, right? So let P of x be a polynomial function. For example, we have 2x cubed minus 5x plus 1. So we say that a root or solution of the equation P of x equals 0 is a number R such that x is equal to R makes the equation true. That is P of R equals 0. That simply means that any value of x that is a root of 2x cubed minus 5x plus 1, if you substitute it into P of x, you get 0. Because that means, and that that's connected with the remainder theorem. So that means there's no remainder, meaning that x minus that value, if the value is c, for instance, if p of c gives 0, that means x minus c can divide 2x cubed minus 5x plus 1 perfectly without remainder. So that's the idea of root or solution. On the other hand, we talk about 0, a 0 of the function f of x. So if you say a function f of x is equal to the polynomial p of x, so its 0 is a number r in the domain of f such that f of r is also 0. So in essence, you can see that the two of them are about the same thing. So in the context of polynomials, we usually set f of x to p of x. So root of the equation p of x equals 0, and the 0, all right, of the function f of x equals p of x are the same concept. They are values of x where the polynomial evaluates to 0. So whether we say root or 0 or solution, we are basically talking about the very same thing, right? We are simply talking about the value of the variable that satisfies the equation in the variable, right? So geometrically, if we think of f of x to be p of x as a graph in the xy plane, right? Zeros and roots correspond to the x-intercepts of the graph, points where the graph crosses or touches the x-axis. So for instance, if we solve a problem and the solutions are -2 and 2, it means that if you plot the graph, the graph is it's going to pass through points -2 and 2 on the x-axis, right? So let's talk about root of the equation p of x equals 0. Root of the equation p of x equals 0. Okay, so consider the polynomial equation p of x equals 0, whatever the degree is. So by definition, a number r, which is real or complex, is called a root or solution of the equation p of x equals 0 if p of r is equal to 0. I mean, we've been seeing that even right from 3 videos back, right? So this is just like deepening our understanding of what we've been doing all along. So what is its connection to factorization? Just like I mentioned earlier, if r is a root of p of x, then the polynomial x minus r is a factor of p of x. That means it can divide p of x without a remainder. Equivalently, we can say that p of x can be written as p of x equals x minus r, that polynomial, multiplied by q of x, which for some polynomial q of x with degree one less than the degree of p of x. Now, in essence, we are saying that if this p of x is of degree 4, so q of x is going to be of degree 3 because the polynomial dividing it is actually of degree 1. So it reduces the degree, and that's why it's easier after you have found one thing that can divide it. It's easier now. Whatever is left can probably, if you have a cubic expression and you find a root for it, so it can easily be reduced to quadratic, which can be better handled compared to a cubic expression. So if it's a quartic expression, once you find a root that divides it, then whatever the q of x is going to be going to be cubic, which makes it a bit simpler, though you may still need to try separate different values to see which one goes into it. Okay, so we have an example, very simple example, by the way. Let p of x be x squared minus 5x plus 6. So solving x squared minus 5x plus 6 equals 0. Of course, we already know that we need two numbers, m and n, such that m plus n is -5, whereas m times n is 6. And, the m and n should be products, they should be value numbers that multiply, that you multiply, so you can obtain them easily from 6. And of course, to get 5, of course, it has to be 2 and 3. And because 5 is negative, then it has to be -2 and -3. So you have x minus 2, x minus 3 equals 0. So in short, if x minus 2, x minus 3 is 0, that means x minus 2 is 0. Either x minus 2 is 0 or x minus 3 is 0, or both of them are 0. So and that gives us x equals 2 and x equals 3 as the solutions. So thus P of x can be written as P of x equals x minus 2 into x minus 3. So that's talking about roots. So like we said, root and function and 0, they actually are the same. So 0 of the function f of x equals P of x. Now if you let f of x be equal to P of x, by definition, a number r is a 0 of the function f if f of r is equal to 0. So since f of x is equal to P of x, this is exactly the same condition. Here, for root, we said P of r should be 0. Okay, but for 0, we say f of r, which is also equal to P of r, should be 0. So it's basically the same thing. By geometry, the graph of y equals f of x intersects the x-axis at x equals r. So I'm going to give a couple of examples as we move on. So the point r, 0 is an x-intercept. Okay, so look at this now. The same equation, x squared minus 5x plus 6 that we just solved up there. So let f of x be x squared minus 5x plus 6 as before. Then f of 2 is 0 and f of 3 is equal to 0. So that is, we put 2 here, that's 2 squared minus 10 plus 6. So 2 squared is 4, 4 plus 6, 10, minus 10, that's 0. If you put 3, that's 9 minus 15 plus 6. 9 plus 16 is 9 minus 15 plus 6. 9 plus 6 is 15. 15 minus 15 is 0. So 2 and 3 are zeros of f of x. So which correspond with the 2 and 3 we got by the time we equate all this to 0. All right. So in that case now, we can then say that the zeros are x equals 2 and x equals 3. The graph of y then, which is x squared minus 5x plus 6, crosses the x-axis at 2, 0 and 3, 0. And that is true. We can easily see that by going to Desmos. Okay, let's go to Desmos and we find that that is pretty true. Okay, so let's plot that. X, so now we have x squared, all right, minus 5x plus 6. So if you expand this now, you see that this curve cuts at points 2, 0 and 3, 0. That's exactly what we're talking about. Don't forget, this is the origin, right? So this curves, it cuts through at those points, and that's the geometry of this idea. Okay, so let's talk about real versus complex roots. Polynomials can have roots in the real numbers R or in the complex number C. Interestingly, I have playlist on complex variables and real. I've done a whole playlist on real numbers, real analysis, that is. So for real roots, a real root of a polynomial P of x is a real number R belonging to R such that P of R is equal to 0. Easy. And then on the graph of y equals P of x in the real plane, the real root corresponds to an x-intercept, which I just showed, on the graph, on this graph. So these are the intercepts right here. And then having talked about that, real roots may be distinct or repeated multiplicity. So like in the case of 2 and 3 now, they are distinct, they are not repeated. So they would have been repeated if the two values are 2 each. Okay, so for instance, P of x is x squared minus 5x plus 6 that we've done. So the roots are x equals 2 and 3. Both are real. But on the other hand, if we have P of x equals x minus 1 squared. So in this case, you have x minus 1 into x minus 1 equals 0. That means x minus 1 equals 0 and x minus 1 equals 0. So you have x minus 1, real root with multiplicity of 2. That means it's occurring twice. So that's x minus 1 squared. So if you take this away and we have x minus 1 squared. So the root is the same in two places. X minus 1 raised to power 2. So you see, instead of cutting through, because this one is, the root is x minus 1, so it turns at x minus 1 because it's double, right? So it just turns there instead of cutting down, right? So that's the kind of thing we have. If you look at this now, what if the root is 2 twice? It just shifts like that. So you just have that shifting going on that way. So you have x minus 1. So if it was x minus 2, like I showed you, if you want to visualize everything together, so I just have 2 here. Okay, so it just keeps traveling like that. So here, if you have x minus 3, so it just keeps going like that, right? So we have that shift going on. So that's for real numbers. On the other hand, we have complex roots. So when do we have complex roots, for instance? Um, Complex or non-real roots. A complex root, okay? A complex root is a complex number z equals a plus bi, all right? With possibly b not equal to 0. So b must not be equal to 0. If b is 0, you can't really say it's complex like that, such that p of z is equal to 0. So in this case, now instead of having p of x or p of r, you now have p of z equals 0. So if b is not equal to 0, the root is non-real, so it does not correspond to any x-intercept on the real graph because we only plot real x value, we only plot real x values like that. So complex roots become essential when we work over C, that's the set of complex numbers, and use the fundamental theorem of algebra. So examples, imagine you have p of x equals x squared plus 1. So if you want to solve this now, solve x squared plus 1 equals 0. That means x squared is equal to minus 1. And by the time you take the square roots of both sides, I mean, it means x is going to be plus or minus I. So in essence, this is what I'm just talking about. Let me go to the worksheet to explain that. So you have x squared, plus 1 equals 0. So, that's x squared equals minus 1. And x now is square root, that's plus or minus square root of minus 1. Here, you don't want to lose anything. Normally, at high school level, this was impossible, all right? But when you get to the university, you discover that, oh, we can say that the square root of minus 1 is I. So you have plus or minus I. And this is what actually complex number is all about. So the whole idea of complex number is that we can say I is the square root of minus 1. And that's where complexity comes in. So you have plus or minus I like this. So you have both roots. I and minus I are complex and they are non-real. So that's one thing. So another thing is you can also do the idea of discriminants. So P of x is x squared minus 2x plus 5, for instance. So you can do the discriminants. Of course, the whole idea of discriminants, I think we talked about it previously, that, okay, this is x squared minus 2x plus 5, right? So, okay. So for x squared minus 2x plus 5, x squared minus 2x plus 5 equals 0. We want to solve this. I mean, the whole idea of discriminants came from this, the so-called almighty formula. I think you can just call it the quadratic formula. So you have plus or minus, I think it's minus b rather, minus b plus or minus square root of, plus or minus square root of b squared minus 4ac, okay, all over 2a. So from this expression now, so we see that from this expression, a is equal to 1. That's the coefficient of x squared. B is minus 2. That's the coefficient of x. And c is equal to 5, right? So for the discriminant, this part is what we call the discriminant. It determines what happens because we're taking square root of that, right? So definitely, if b squared minus 4ac, so b squared minus 4ac, if it's less than 0, so we're going to get complex, right? We're going to get complex roots. All right. So, but then if b squared minus 4ac is equal to 0, we're going to have we're going to have how do we put it now? Repeated real roots, And finally, if b squared minus 4ac, this is what you call discriminant now. Discriminant. B squared minus 4ac, if it's greater than 0, then you have distinct real roots. In fact, I think there's a whole playlist, a whole video rather, talking about these complex things. So as far as this one is concerned now, so we can say that b squared minus 4ac here is, so based on this, our d here is equal to minus 2 squared. That's b squared minus 4. A is 1, C is 5, okay? So D is equal to 4 minus 20. So D is equal to minus 16. So because minus 16 is negative, it's less than 0. So definitely we're going to get complex roots here. So, I mean, if we can take that on, so, and we say that x now is equal to minus b. B is minus 2, right? So we have minus 2 plus or minus square root of b squared minus 4ac. We already know b squared minus 4ac is d. You know, d now is minus 16 all over 2 times 1. Okay, so x now is 2 plus or minus square root of minus 16 all over 2. So here we have x to be 2 plus or minus 16 is same as root 16 times root minus 1. You know, 16, that's from the rule of sword, right? So root 16 times root minus 1 is root minus 16. This over 2. So now we say x is equal to 2 plus or minus. Square root of 16 is 4. Square root of minus 1 is I, or j sometimes, depending on who is talking. For electrical engineers, they would rather call it j because I represents current most times. So now you have x is 2 plus or minus 4i. I mean, okay, 2 plus 4i all over 2, or 2 minus 4i all over 2. So if you do all that, further you get 1 plus 2i, or you get 1 minus 2i. So these are the two complex roots in this situation now. So that's the idea there, complex roots. So you have 1 plus or minus 2i. So again, both are non-real complex roots, okay? So we go on to talk about conjugates, conjugate pairs. That's for real coefficient polynomials now. So we can have actually conjugate pairs. Now you see, what we got already is what you call the conjugate pairs, because you have two of them are the same except for the sign. So you have 1 plus 2i or 1 minus 2i. So this is a pair. And what makes them conjugate is that one is positive and the other is negative. That's the basic idea of conjugates. That's the idea of conjugate pairs, right? So complex conjugates, real coefficient for real coefficient polynomials. If the polynomial p of x has real coefficients and has complex, that is non-real roots, a plus bi with b not 0. But of course, if b is 0, then it becomes real, right? With b not 0, then its complex conjugates a minus bi. So you see, root a plus bi. Then its complex conjugates a minus bi is also a root, right? So once a plus bi is a root, its complex conjugates a minus bi is automatically a root. If a minus bi is a root, then its complex conjugate a plus bi is also a root. So non-real roots of real coefficient polynomials come in conjugate pairs. So every time you do anything that involves complexity like this, you see they always come in this form. So you have all the numbers are the same, except that one is positive and the other one is plus here, the other is minus, or minus and up and plus. So that's conjugate, the idea of conjugate pairs. So for p of x equals x squared minus 2x plus 5, one root is 1 plus 2i, the other root is 1 minus 2i. So these two roots form a conjugate pair, right? So we move on to degree of a polynomial and maximum number of roots, okay? We're still going to talk about some of the things we come across here in some depth as we move on. So degree of a polynomial and maximum number of roots. So let p of x be a polynomial of degree n, that is the highest power of the variable, or the total degree of the variable is n. That's what makes it the polynomial of degree n. That is, n is greater than or equal to 1, of course. If n is equal to 1, that's linear, right? But once it is 2 upwards, that's quadratic and so on, and with complex coefficients. So if you have p of x, a polynomial of degree n with complex coefficients, then we have the fundamental theorem of algebra, FTA. And what does it say? Every non-constant polynomial of degree n with complex coefficients has exactly n complex roots, counting multiplicities, right? So counting multiplicity means that a repeated root is counted as many times as its multiplicity. So if you have 1, if you have 1 as a solution 3 different times, then we count it 3 times. So this root may be real or non-real complex numbers. So we can talk about example of multiplicity. Interestingly, in the next video, we'll be talking about multiplicity in some depth, right? So example multiplicity, consider p of x equals x minus 1 squared into x plus 2. So if you solve this now, you see you have x equals 1 twice. So and x equals minus 2 once. So root x equals 1 has multiplicity of 2. Root x equals minus 2 has multiplicity of 1. So total number of roots counting multiplicities will be 2. The 2 times 1 appears, and 1 appear, and the 1 time minus 2 appears. So the total multiplicities will be 2 plus, total number of roots counting multiplicity will be 2 plus 1 equals 3. So the degree of P of x is 3, matching the fundamental theorem of algebra. In short, it's easy to know the number of solutions you're expecting once you see a polynomial. Once you see a polynomial, its number of solutions is equal to the degree of that polynomial. So a quartic polynomial, you expect to get 4 solutions. A quintic polynomial, you expect to get 5 solutions, like that. That's for a quintic, yeah. That's 5, I think, yeah. So maximum number of complex roots. So for the FTA, from the fundamental theorem of algebra that we saw up there now, all right, from that FTA, right, from that, we see that a polynomial of degree n has at most n distinct complex roots. It can have fewer if some roots are repeated, okay? So for complex roots now, for distinct complex roots, a polynomial of degree n has at most n distinct complex roots. It can be fewer if some roots are repeated, so that works. Then talking about maximum number of real roots. So because real numbers are a subset of complex numbers, a polynomial of degree n has at most n real roots. So in a way, we can even say every real number is complex in the sense that if you have 4, which we know to be real, you can simply say it is 4 plus 0i, So it's like complex, all numbers are complex. Then we can now begin to distinguish it, talk about real and everything. So it might have, so we see that real numbers are a subset of complex numbers. So a polynomial of degree n has at most n real roots. So it might have fewer real roots. The rest, if any, are non-real complex roots. So imagine this expression now. You have x cubed minus x. So first of all, we learned factorization, right? So the first thing you want to do is, okay, I think I need to work on this. P of x equals x cubed minus x, right? So we have P of x equals x cubed minus x. So the first thing we want to do, okay, let's even equate that to 0. So it means that first thing we want to do is x is common to both, so we can factor that out. So that's x squared minus 1 equals 0. Now you see this is difference of 2 squares because it's the same thing as x into x squared minus 1 squared. So that's difference of 2 squares. And we learned that in a previous video that we can easily say this is x now into x minus 1, x plus 1, and that is 0. So if you equate everything to 0, so it means x is equal to 0, or x minus 1 equals 0, or x plus 1 equals 0. Okay, so that means you have x to be 0, or x is equal to minus 1, or x is equal to, x is equal to plus 1, or x is equal to minus 1. So x is, you have it in this as 0, 1, minus 1. Anyhow you want to arrange that, okay? So we have that going on there. So in this case now you see, of course, because it has degree 3, you expect 3 roots. Whether repeated or not, you expect 3 roots. So real roots are minus 1, 0, and 1. So all the roots are real in this case. There's no complex. So they have 3 real roots, all distinct. So maximum of 3 real roots attained in this situation now, okay? So what if we talk about x raised to power 4 plus 1? See, x raised to power 4 plus 1. The degree is 4 already, so we expect 4 solutions. So in this case, no real roots since x raised to power 4 is greater than or equal to 0 for all real x, right? So x raised to power 4 plus 1 is greater than 0. So we don't expect any real roots here because x raised to power 4 is already greater than or equal to 0 for all real values of x, right? So x raised to power 4 plus 1 is greater than 0. So all 4 roots are complex and non-real. So, I mean, we can attempt looking for solutions and all of that, right? Well, I'll just leave it the way it is here. Then, I mean, in subsequent videos, we'll look deeper into some of these issues. So now, looking at the third one, you have x minus 2 raised to power 3, right? So that's degree 3 automatically. So that's degree 3. And here you have only one distinct real root, x equals 2. But it occurs 3 times, so it has multiplicity 3. So root x equals 2 is counted 3 times in total of 3 complex roots, okay? So summary checklist for everything we've been talking about. First of all, we see that the root of equation P of x equals 0 is also the same thing as a 0 of the function f of x equals p of x, right? So that's why you can say that the solution to a polynomial can be, you can call it the root, you can call it the zero, you can call it the solution, right? So real roots implies that x-intercept of the graph y is equal to p of x. That is settled. Then complex non-real roots implies that no real x-intercept but still a solution in the complex plane. For real coefficients, non-real roots come in conjugate pairs, a plus bi. That's what we say, we call them conjugate pairs. The only difference is the change in sign, that's all. So a degree n polynomial has exactly n complex roots counting multiplicities, has at most n distinct roots, or has at most n real roots, at most, right? So in this case now, I mean, this first statement can be taken to be the whole idea of has exactly n complex exactly n complex roots counting multiplicity. That means that even the real roots you get, you can see them as complex numbers, because real numbers are subsets of complex numbers. So we have some practice questions here. I don't know. Okay, the first one has already been taken care of. It's pretty straight to the point. So it says, let p of x be x squared minus 5x plus 6, and f of x equals p of x. Find all roots of the equation, blah, blah. Think that's already settled, so I may not have to worry. Okay, maybe I should try question 5 now. Question 5 says, let p of x be equal to x raised to power 4 minus 5x squared plus 6. Solve p of x equals 0 by factoring. Okay, I want to solve by factoring. Then verify that the total number of roots counting multiplicity matches the degree of the polynomial. Of course, that is what's going to happen. So x raised to power 4 minus 5x squared plus 6. Okay. So now we're talking about x, p of x equals x raised to power 4 minus 5x squared plus 6. So looking at this question the way it is, you can already solve it. You can solve it in different ways, right? Based on what we had learned previously. Then it says classify each root as real or complex, verify that the total number of roots. Okay, we'll come to that. So first of all, we want to solve p of x equals 0 by factoring, okay? So that's a now. So a okay. So I come for a to solve p of x equals 0 by factoring. So I'm thinking of what to do here. Well, I mean, one way to do it is you can see x squared, x raised to power 4. So we can actually substitute to reduce the power, or we can actually go factoring straight. For instance, if I put 1, right? Or if I put minus 1, doesn't change anything really. Okay, let me use a method, something I'm convinced about. Okay, so look at this now. So want to solve p of x equals 0 by factoring. Okay, so I have p of x equals 0. That means that we have x raised to power 4 minus 5x squared plus 6 equals 0. So because this is even power here, so it's easier to substitute. We did that in a previous video, by the way. So we can say let u be x squared. So if u is x squared, we know this is going to be x squared squared. X raised to power 4 is x squared squared minus 5x squared plus 6 equals 0. So this is easier to handle this way. So we now have, so x squared is u, so we have u squared minus 5u plus 6 equals 0. So doing it this way, it makes it pretty easy to handle. So we need two numbers to multiply to get 6, but when we add, we get minus 5. So we have u squared. So 2 times 3 is 6. Then if you can say minus 2u minus 3u, that gives us minus 5u plus 6 equals 0. Okay? So we can then group, we have u squared minus 2u together, then minus 3u plus 6 together equals 0. So you have u into u minus 2, minus 3 into u minus 2, and that is equal to 0. Okay? So this is u minus 2 into u minus 3 equals 0. That means u is equal to 2 or u is equal to 3. Now, don't forget we didn't start with u, so we have to remind ourselves that, but u is equal to x squared, but u is equal to x squared, right? So remembering that now, that we know that it means that x squared is equal to 2 or x squared is equal to 3. So if that is the case, it means that we can say that, okay, x squared is 2 and x squared is equal to 3. So we can simply say that x is equal to plus or minus, x is equal to, yeah. So x is equal to plus or minus 2 root 2, or x squared is equal to plus or minus root 3. Okay, so we have solved the problem like that. So, okay, this should be x. This should be x because we're taking the roots. So, in short, altogether we say x is equal to plus or minus root 2 or plus or minus root 3. So these are the four solutions. No, plus root 2 is one, minus root 2 is another one, plus root 3 is one, minus root 3 is another one. Okay, so with that in place now, what does the second part ask us to do? The second part says we should solve, okay, solve P of x by factor. We've done that. Classify each root as real or complex. Okay, classify each root as real or complex. Well, all the roots are real. Okay, all the roots are real. All, that's B now. All the four roots, all the, okay, let me just say all the roots are real. All the roots are real, settled. And then we can have the last one, which talks about making sure that the root is equal to the number of degrees. I mean, the degree of the polynomial. Verify that total number of roots, count multiplicity matches the degree of the polynomial. First of all, there are no multiplicities here, because all the three roots are distinct. Okay, see, since the roots are plus root 2 minus root 2 plus root 3 minus root 3, they are 4. They are 4. Uh, uh, they are distinct. Let me just start with that. They are distinct. So they are all different for sure. They are distinct and they are 4. Okay. As such, they tally the number of roots, the number of roots tally with the degree of the polynomial, with the degree of the polynomial. So basically, we have taken care of that idea. All right. So that goes. Yeah, so we can come back here and round off. So see question 1, 2, and 3. Then question 4, 5, and 6. You want to try your hands on them. Question 4, 5, 6, and 7. Then we have question 8, 9, and 10. So on this note, I come to the end of this interesting video about roots and zeros of polynomials. So here now we see that x is equal to 1 with 3 multiplicity of 3, x is equal to minus 2 with multiplicity of 2. So it says find all roots and their multiplicity. So this is already done for you, just equate to 0. So you have x equals 1 thrice, x equals minus 2 twice. What is the degree of the polynomial? The degree of the polynomial will be 3 plus 2, 5, right? So it's just sum of these multiplicities, you get 5. How many distinct real roots does P of x have? So there are only 2 distinct roots, but they have multiplicities. Does P of x have any complex or non-real roots? No, all of them are real, okay, because we don't have anything like square root of negative here. All right, so that's it as far as this video is concerned. Let me know how helpful this is for you. If there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I thank you very much. If you haven't subscribed, what are you waiting for? Why not go ahead and subscribe right now and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of my channel by clicking on join, and you see 3 levels of membership there, and each of them gives you a special privilege. At the highest level, you have a privilege of hanging out with me in a physical location if we are together in the same space at any point in time. And if not, we can hang out together online to discuss anything that interests you on my channel, be it mathematics, data analysis, data science, scholarships, writing books, machine learning, whatever interests you on this channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Watch out for multiplicities, some more depth on multiplicities in the next video. Bye.